So today we shall discuss optimal binary search tree. So the optimal binary search tree is a problem wherein we are given n keys a1 to an such that a1 is less than a2 and so on till an minus 1 is less than an with the respective probabilities p1, p2 and so on till pn, and such that p1 is less than p2 and p2 is less than p3 and so on till pn minus 1 is less than pn. So in searching for a key, we find a binary search tree with a minimum average number of comparisons in case of a successful search. Basically, binary search trees are used to implement dictionaries. So some set of operations that can be performed on dictionaries are searching for a key, inserting a key and deleting a key. So for example, let us assume that there is a binary search tree with elements A, B, C and D in it. So there could be several different binary search trees for these elements. So for example, given elements A, B, C and D, we can have a binary search tree of the manner A, B, C and D. Or we can have a binary search tree of the manner B, A, C and D. Or you can still have a binary search tree of the manner C, B, A and D. So you see that given 4 elements, it is possible for me to draw more than one binary search tree. Thus, how many binary search trees can be drawn with n keys? Therefore, total number of binary search trees with n keys is equal to the nth Catalan number given as C of n is equal to 2ncn divided by n plus 1. So in this example, C of 4 is nothing but 14, which says that we can draw at the most 14 different binary search trees if you have 4 elements. So when you are trying to search for a key, the number of comparisons depend on the level of the keys. So for example, we have drawn a sample binary search tree here. So we say that the root of this binary tree is at level 1, the root of the node B and D is at level 2 and similarly A is at level 3. So searching a key A requires a total of 3 comparisons. Searching a node A in this binary tree requires a total of 3 comparisons. So what is the cost of this search? So it is given by the expression summation of levels into their respective key probabilities. So C is at level 1 into the probability of finding C is 0.4 plus 2 is second level wherein we have 2 keys, so 2 into probability of B is 0.2 plus probability of D is 0.3, which is added with level 3 and the probability of finding A is 0.1. So the total number of comparisons in order to find a key A is obtained as 1.7. So similarly, as I have told you that we can have multiple different binary search trees, one more example could be we can swap A with B. So let us say A is placed here and B is placed here. So now what is the cost of finding B? So here C is at the location at the level 1. So 1 into its probability 0.4 plus 2 level 2. On level 2 you have key A and D. So probability of A is 0.1 plus 0.3 plus level 3 into probability of B is nothing but 0.2. So the cost or the expected number of comparisons for this binary search tree is obtained as 1.7. So therefore you can imagine that there could be 14 different values in this case. Out of these two binary search trees, we find that the first example yields us a minimum cost that is 1.7. So therefore, we call it to be an optimal binary search tree because the number of comparisons are less. But it is not the optimal binary search tree from among all 14 possible binary search trees, because we have not drawn all 14 binary search trees and not calculated the expected number of comparisons. But it is not possible to construct binary trees and compute their costs and find the optimal binary search tree, that is for all 14 possibilities. Instead, we try to apply dynamic programming approach to find the cost of all 14 binary trees. Using a tabular method, we can directly generate Using a tabular method, we can directly generate the cost of binary search trees and also find the roots and find which is the optimal binary search tree. The recurrence relation for optimal binary search tree is given as C of ij is equal to minimum among C of I, k minus 1 its minimum among C of I, k minus 1 plus C of k plus 1 j plus summation of probabilities, wherein for I and j ranging between 1 to n and k ranges between I and j. So C of I is simply assigned the probability of the node I. Again here I ranges between 1 to n. So C of I is equal to Pi is nothing but the cost of one node binary tree. It is the cost of one node binary tree. And C of I comma I minus 1 is equal to 0, which stands for number of comparisons in empty binary tree. So C of I comma I minus 1 is nothing but one example is C of 1 comma 0. If i's value is equal to 1, then C of I comma I minus 1 is C of 1 comma 0, which is set to 0. So similarly C of 2 comma 1 is set to 0, C of 3 comma 2 is set to 0. So it means that all the diagonals in this tabular column are set to be 0. And what you observe is C of 1 comma 1 is the probability P1. C of 2 comma 2 is the probability P2. That is C of I comma I is a probability Pi. and the rest of the things are obtained by the recurrence relation. And our goal is to find the minimum cost which is obtained at the intersection C of 1 comma n. So let us say we are given with keys A, B, C, D and their respective probabilities are 1, 0.1, 0.2, 0.4 and 0.3, and we are supposed to prepare two tables. One is the cost table and the other one is the root table. So this table tells us the minimum cost of finding a key, and this table gives us what should be the root of the binary tree. So let us start filling this table, the cost table, by using the recurrence relation. C of ij is equal to min of C of I comma k minus 1 plus C of k plus 1j plus summation of the probabilities. Let us look into this problem step by step. So initially the cost table is filled with the diagonal values as 0, and then C of 1 comma 1 is C of 1 comma 1 is probability of 1 P1, that is 0.1. C of 2 comma 2 is the probability of the second element, that is 0.2. C of 3 comma 3 is the probability of third element, 0.4, and C of 4 comma 4 is the probability of the last element, set to 0.3. So now the first step here is to fill the diagonal elements with zeros. Second step is to fill C of ii with pi's, and the third step says that k stands for the root of the tree, and therefore you are supposed to fill the value of k in R of ii. Initially, R of ii, that is R of 1 comma 1, we set it as 1. The rule says that R of ii should be set to I. So therefore the root of 2 comma 2 is set to 2, root of 3 comma 3 is set to 3, and root of 4 comma 4 is set to 4. So the fourth step is to find the cost of a binary search tree that has only 2 keys in it. So now we are supposed to find out a binary search tree which has only 2 keys in it. So therefore we are now supposed to find out C of 1 comma 2. So C of 1 comma 2, wherein 1 is I and 2 stands for J. So we try to find a minimum value where k ranges from I to j, that is k ranges from 1 to 2. For the value of k, when it is 1, we have C of I is 1 and k minus 1 becomes 0, plus C of k plus 1, so k is 2, k plus 1 is, so k is 1, so k plus 1 is 2, comma, j's value is also 2. So it becomes C of 2 comma 2 plus summation of probabilities where S ranges from I to J. So I's value is 1, J's value is 2. So therefore sum up P1 plus P2. So therefore get these values from the table, the cost table, sum them up. So you have 0.5. So when the value of k becomes equal to 2, then the same recurrence relation now becomes C of I is 1, comma, k is 2, so k minus 1 is 1, plus C of k plus 1, k is 2, so k plus 1 is 3, comma, j's value here is 2, so plus p1 plus p2. So C of 1 comma 1, C of 1 comma 1, we have a value 0.1, plus C of 3 comma 2, you have a value 0, plus the probabilities p1 and p2 give us a value 0.0. So among 0.5 and 0.4, we find that 0.4 is a minimum value. So therefore, we put value 0.4 in the table at the location C of 1 comma 2. At the location C of 1 comma 2. Right? So similarly, try to find out the cost of all possible 2 key combinations. So once we are done with finding the cost of 1 comma 2, the next time we try to find out the number of comparisons for a binary tree which has only 2 keys, that is 2 and 3 in it. So therefore, second time you are going to find the cost of a binary search tree with only 2 keys, that is B and C in it. So again, apply the same recurrence relation here. So I is nothing but 2. I is nothing but 2. J is 3. So K is 2. For the first time when the k is 2, then the recurrence relation becomes C of I comma k minus 1. So C of I is 2, k is 2, so k minus 1 is 1, C of 2 comma 1 plus C of k plus 1 is 3 comma j is also 3, so C of 3 comma 3 plus the probabilities of two elements, that is p2 and p3. So substitute the values from the table, you get a sum value as 1. For the next time, set k's value as 3 because k ranges from I to j, and then this time you have C of 2 comma 2 plus C of 4 comma 3 plus P2 and P3. So you get a new value of 0.8. So among these two, the lesser value is 0.8. So you set this minimum value into the location C of 2 comma 3. Similarly, in the root table at the location R of 2 comma 3, set the value of root to be equal to 3. That is, you get minimum number of comparisons to be 0.8 when the root of the tree is 3. So similarly, the next time again try to find out the cost of binary tree which has only 2 elements C and D in it, that is 3 comma 4. So once you are done with finding the cost of binary trees with only 2 keys in it, the next time try to find the cost of binary trees which has 3 keys in it or 3 elements in it. So C of 1 comma 3. It means that this binary tree has elements A, B and C in it. So apply the same recurrence relation, but whereas the k's value here now ranges between 1 to 3. Substitute the values. I am not substituted them here. You substitute the values from the table and you see that the minimum value that you get is 1.1. So put this 1.1 in the cost matrix at the location C of 1 comma 3, and in the root matrix at the location R of 1 comma 3 put the value of k as 3. So once you are done with finding the cost of binary search trees with 3 possible keys, the next time try to find out the cost of a binary search tree which has all 4 keys in it. So again apply the same recurrence relation. Here i's value is 4 and j's value is, i's value is 1 and 4's value, j's value is 4. So k ranges from 1 to 4. So in this step you obtain a minimum value to be 1.7. So put this 1.7 in the cost matrix at the location 1 comma 4 and k is equal to 3, for which you have obtained the minimum cost to be 1.7. So therefore insert 3 in the location root of 1 comma 4, that is in the root matrix. So this is the algorithm to find out optimal binary search tree. So the very first step here is we set 1 comma 2, 1 comma 0, 2 comma 1, 3 comma 2 etc. as zeros. Then we set the diagonals with the probabilities, and in the root table also we set r of I comma I as 1. So all the prerequisites of setting up a table are done here. And then here minimum value is set to infinity. How do we obtain the minimum value? So using the recurrence relation, that is C of I comma, we obtain the minimum value with the recurrence relation C of I comma k minus 1 plus C of k plus 1 comma j. So if it's a minimum value, then just put it into, calculate the sum of the probabilities and put it into the location C of ij. So this for loop, this if statement runs for k number of times. That is, k ranges between I to j. For the first time, if k's value is if i's value is 1 and j's value is 2, then this particular if statement runs for once when the k's value is 1 and for the second time when the k's value is 2, and from among these two values, whatever is the minimum value you get should be set into the variable mean value. So and from which root have you obtained this mean value has to be set into the variable kmin. So kmin is set at the location r of I comma j in the root table. Similarly, after obtaining this mean value, we sum up the probabilities, which we already have it in the variable sum, right? So this for loop tells us that for the first time it is going to calculate the cost of binary search trees with only 2 nodes in it. Next time it will calculate the cost of binary search trees with 3 nodes in it. The next time the 4 nodes in it. Right? So therefore, lastly, it is going to return us the value that is at the location C of 1 comma n, that is the final cost of finding a key, and it also returns us the root of the binary tree. So therefore we say that the time efficiency of this optimal binary search tree is given as theta of n cube because of 3 for loops in it. Thank you.